Cominciamo? Okay, sorry. So I was telling you that we may add these two interactions to break either the time reversal symmetry or the U1 symmetry. So I'm opening two gaps in two different ways. And I want to understand what happens to this interface. My aim is to show you that there will appear some edgemont, some Majorana bound at that point. And to understand this, the better way is to write down the Popoli-Bosdejan Hamiltonian. In particular, I chose a basis, a number basis, which is C up, C down. Actually, I suppose it is minus so this is the basis that I'm using with this strange exchange to simplify the calculation. And essentially, once you consider a mode which is a linear combination of these fields, you want to understand what is the commutator between the mode and the Hamiltonian that we wrote down, considering the sum of these terms. And this is given by the Hamiltonian, which is a 4 times 4 Hamiltonian, which essentially reads the x and here so the calculation you obtain is Hamiltonian. You may see it as a block Hamiltonian, in which of diagonal you have the parent terms, the square parent terms, and instead the two diagonal blocks you have the single particle physics. And now I want to analyze separately what happens on the right and what happens on the left. So when delta is on but m is off, and vice versa when m is on and delta is off. And in particular, I apply a simplification, so I consider that instead of having maybe this system, we have a system where the two things touch. So we have here delta strong and then m equal to 0, and here instead m strong and delta equal to 0. So this is the ferromagnet, this is the superconductor, and in the middle there is wedge. So let us consider the physics here. You see that n gets to 0, so these things are decoupled into blocks. The first block will have e the x, then the minus e the x, and the other block is essentially the conjugate of the first one. And we are hunting for zero energy modes. Essentially, I would like something such that h Bosdejan for a vector gamma must be equal to 0. So I solve this equation in the regime where m is equal to 0, and you see that since I have two blocks, I simply can consider this simple matrix. Zero, and by solving this, I simply obtain that a will be written minus y minus integral of delta over the x prime from 0 to x, and instead it becomes the same exponential. And so if I consider the blocks and I things carefully, I obtain essentially that there appear two modes on the right that correspond to a bound state that I can write like gamma right equal to minus r psi up times the minus integral minus sit down dagger equal the minus the same integral. So, and then I will have gamma up dagger, which is equal to up dagger is exponential minus down and is exponential. So here I have a bound state really. It's not a zero energy mode like before. So I have two different modes. These are fermionic modes, but they live only on the left. So here I have first bound state essentially. And I can do the same computation on the left. Also on the left, the big 4 times 4 volume of the General Hamiltonian decomposes into blocks. And I obtain that now the I have that n is greater than 0 and delta is equal to 0. The equation that we have to solve are these ones. And in this case, I obtain similar results, namely C equal to I e to the integral m over the x, and d is simply the integral. And so you see that here we have a length, an exponential decay, which is dictated essentially by this ratio, and here we have an exponential decay, which is dictated by this. And also in this case, I will obtain thus two left operators, gamma left and gamma left dagger, which are say up equals the exponential, say down equals the exponential, and here the complex conjugate. So also in this case, I have another bound state which is localized in the interface. So here I have a bound state with gamma left and gamma left dagger, which create or annihilate fermion in this bound state. And here instead I have gamma right and gamma right dagger, which create or annihilate fermion in here. However, I have also the interface. So I must impose some continuity equation for x equal to 0, because these two objects are defined only on the left, same line and on the right part of the system. So I must impose essentially that for x equal to 0, I have that alpha gamma right plus beta gamma right dagger must be equal to gamma left plus delta gamma left dagger. This is a boundary condition that I want to fulfill to obtain essentially modes that are 0 modes in this interface. And if you write down this in terms of the vectors in this basis, you essentially obtain that this part will obtain something of the kind of alpha minus I 0, 1, 0 plus b 0 minus 1, 0 I equal to gamma plus delta minus 1 on this side. You can solve this, and in the end of the day, you will obtain that the only operator which survives is an operator gamma, defined now on the full line, which is equal to gamma right plus gamma right dagger plus gamma left plus gamma left dagger. So that this is for x greater than 0, and this is for x smaller than 0, and x equal to 0, they match. But this is a real operator, so essentially, you gamma square, this is equal to 1 once you normalize. So you may demonstrate that this is a Majorana zero energy mode, which is localized in this interface. So it's a zero energy mode because we built it in such a way that it commutes with Filippo Hamiltonian. It is localized because it has these exponential days on one side and on the other, and you may easily see that it is real. So in the end of the day, if we go back to this system, we can also consider further complication, but the important thing is that there exists a single Majorana zero mode, which is not anymore a bound state, it's just a single mode. I do not have a gamma dagger pair, I have just this real gamma, which works exactly as the gamma left and gamma right that we wrote for the interaction. So this is a possible recipe to obtain Majorana zero energy modes, and as I say, we are playing with this edge of the topological insulator and these two ways of actually getting out these gapless edges. Someone before asked me why I was considering the topological insulator. This is why essentially I want to remain only with two fermionic species and not four. If I consider a while, I would like also to have C left down and C right up. The effect of the topological insulator is to gap out these two edges and be left only with this physics. So on the experimental side, there are a few groups that are starting to work with this hybrid structure of topological insulators and superconductors, and some first preliminary result was obtained by Will and well, if you're interested, I can give you the references. But so far, of course, no one still has obtained Majorana in this way, even though there are people working on experimental setups that are very close to this moment. So, at the moment, we considered all these Majoranas as being far away and decoupled, and so I told you that in the thermodynamic limit, their interaction is small in such a way that the symmetry that we had before is a symmetry and this will degenerate. Actually, however, once you start to consider this physics with superconductors, for example, you have to be careful because there are some interactions that may come into play. And especially, I would like to focus now on two of these interactions that affect this Majorana zero energy mode that requires some energy somehow. And the first effect that I want to consider is the fractional Josephson effect I was mentioned before. So we change slightly our setup. We go back to a description in terms of type chains, let's say. But now I want to consider what are the phases of superconductors. That, if you remember at the beginning, I told you when it was Gauge transformation, we erase this phase and nothing happens. The reality is not really so. So let us consider a system with two superconductors. One is here, one is there. You may imagine this like the deltas equal to T in the type chain at the beginning. So imagine to have the type chain here, the type chain there, and we are in the topological phase here and the topological phase there, in such a way that we have some uncoupled Majorana mode on this point. Imagine, for example, that maybe no is equal to 0 and no is equal to 0. But, so I will have some Hamiltonian, which is the Hamiltonian of the type chain on the left, plus the Hamiltonian of the type chain on the right. But the important thing now is that I want to consider here the delta, which delta tilde, which is delta E di left. And here delta tilde, which is delta E di right at this point. And in general, of course, we can do gauge transformation, but left minus P right can be considered as a gauge invariant phase difference. So, for example, I can do a gauge transformation with this in the right minus P left. That one is real. Furthermore, I want to consider a situation in which somehow these two superconductors are closed, or these two fermions may interact with each other, so that I have some tunneling term. And this tunneling term acts as an interaction of this kind, so on the steep dagger and of the left chain, see one of the right chain plus the left. So at the beginning we saw that I was mapping essentially to get rid of these phases, see, into I phase over. This amount to say that I can rewrite these two operators like C and the other. Let us go back to this case. So that here we have that C dagger n of the left chain is equal to the I over 2 divided by 2 gamma minus 1 plus I gamma 12. And the same way, 1 will be equal to 1 gamma over 2 gamma 1 minus so I have that inside this term there appears a phase difference which is going like left minus P right over 2. This over 2 essentially means that instead of having a tunneling of a Cooper pair, like what is usually done in superconductors, here this term is just a tunneling of a single electron. So you have to imagine that in the case of normal superconductors without any sort of topological phase, this term would be strongly suppressed because to change the fermionic parity of this superconductor and that superconductor, I have to break two pair pairs and I pay an energy price which is proportional to this delta. Instead, in the topological phase, you know that there are these zero energy minor modes. And in particular, you can calculate all the terms in terms of the gammas appearing here. And among all the terms, there is one which does not break the pairs appearing here and there that are strongly connected. So they involve only the zero energy mode. So if you do perturbation theory of this interaction term, there is only a single term which survives.
So you repeat why you do perturbations?
Sorry?
Why you do perturbations?
Because I am assuming essentially that I am in a regime in which this delta equal to t is much stronger than mu, and this delta equal to t is much stronger than mu, and it is much stronger also of this j. So to grab the physics of the low energy sector, I guess that perturbation theory is the simplest way. Otherwise, you will have to consider the possibility of breaking these pairs. But in general, if you break this pair, which is linked by a strong delta, you pay a 9 energy price. So you see that here, if I consider all the products, I will have terms in I, gamma 1, gamma 2n minus 1. And since gamma 1 and gamma 2n minus 1 are zero energy modes, this is not breaking any of these pairs, and it is safe. It does not change very much the energy, only over scale j. Whereas all the other terms that are, for example, gamma 2 times something, or gamma 2n, no, sorry, this was the 2n minus 1 times something. This implies that I am changing the fermionic parity of this pair and of that pair, and they are required to go essentially from the protected states that are low energy to the continuum on top. So that's why what I want to tell you is that if you consider only the terms which survives, we will obtain that this tunneling Hamiltonian is reduced to simply a term which is J over 4 by gamma 2n gamma 1 times, however, we have dependence on these phases, and this dependence becomes the cosine of phi left minus phi right over 2. So, the interesting thing is that if you change phi r, or the left of the same, into phi r plus pi, the Hamiltonian somehow does not change. But here, as an effect of these two, we are changing the sign of this term. So we are not going back to the same Gauss state as before. Essentially, if this fermionic parity gamma 1 is equal to 1 for this difference equal to 0 for some value pr, once I move to, and this is the ground state, because let us put a minus sign, imagine that this cosine is positive, and I obtain that this is the ground state. If now I change some magnetic flux in this setup, so I add, for example, a magnetic flux here that changes this difference. I add a single magnetic flux of the kind Hc over 3. This Hc over 3 corresponds to adding P5, the phase PR plus 2 pi, and I obtain, however, that now the sign of this cosine is flipped because I'm adding here plus pi. And this state, which was the ground state before, now is the excited state. And whereas the ground state is given by the opposite value. So you have these two degenerate, almost degenerate, well, two ground states that have a difference in energy, which is J over 2. And if I write P of R of a quantity which is 2 pi, I start from these states that have an opposite equivalent parity, y equal 1, z equal -1, and I'm converting them. Then, if I add another pi, so another magnetic vortex, I go back to the initial configuration. However, even though I am closing this energy gap, I cannot have tangents between one and the other state unless I change this fermionic parity. So we are more or less in the same situation that we were discussing before, where to break the conservation, the information that I'm putting here, I need some term which is not quadratic in the gammas, but must be given by a single gamma of this kind. So this is called a fractional Josephson effect because if you observe, for example, the current from this superconductor to that superconductor, this current has a phase which is 4 pi and not 2 pi, like the one that you usually would have for normal superconductors. It is more or less what I was telling you at the beginning, that since we are adding ampere Majorana modes, I can somehow have processes in which a single electron tangents instead of per pair, and I can look into these different periodicity in the current that I'm going to measure. So what I want to say to tell you is that the Hamiltonian is invariant by this transformation, but the ground states and all the observables are not. The ground states and all the observables are invariant by a transformation which sends phi r into phi r plus 4 pi. So that once you have a system with two topological phases belonging to two distinct superconductors, the take-home message is that I must consider some interaction of this kind. Of course, I will have also the interaction given by the usual tunneling of a Cooper pair, which may be written also in terms of Hamiltonian. But this interaction is essentially of an higher order because I need to send 2 electrons from that side. So usually it is believed that under several experimental hypotheses, this tunneling of single electron should prevail over the Cooper pair tunneling, which however does not affect my topological degrees of freedom. So if you are brave enough, but I will not do it here, you can also describe the same model in terms of bosonization, and you will obtain the same result. The second interaction instead is trickier. So the key of this interaction is that I cannot really change this coupling constant J because it is something that in a lab is fixed by the geometry of this structure. Whereas the next interaction that I'm going to introduce has a wonderful property that can be easily tuned, which is very useful if you want to manipulate these systems. And well, this interaction is given by the charging energies of the superconducting ions. And I feel I must go a little bit faster. So let us consider now another superconducting island. I have some way, either the topological insulator edge or the nanowire. In such a way, in this superconducting island, I have 2 ampere 0 modes, gamma left and gamma right. And let us assume that here I have some strong Josephson tunneling energy, EJ, which couples this small superconducting island with a big superconductor, which plays essentially the role of the power vectors. In particular, if I consider small phi is the phase difference between the 2 superconductors, I can write this Hamiltonian as being charging energy of the, let's say, the number of prepared plus some Q induced, plus now I will have here the charge of the Majoranas essentially. So this is equal to I gamma left, gamma right squared plus J, which is this couple with the big superconductor, cosine of this phase difference, which is this is a normal Josephson junction. From here to here, only Cooper pairs may tunnel, not a single point, because the Majoranas are far from the other superconductor, which is not so logical. Here I am a bit cheating because actually the Majoranas are neutral, so they should not have a charge. But this term up here, due to the boundary conditions that you have to consider for these superconducting islands once you vary this phi of phi. So believe me that in the end you will obtain effectively some Hamiltonian of this kind. And well, in the latest 10 years, these structures without the Majorana have been studied carefully. And in particular, there is a special system called the transmon that is described by this Hamiltonian in the regime in which EJ is much greater than EC. So say that experimentally this ratio is of the order of 50. And in this case, the interesting thing is that we can apply some sort of semi-classical approach to understand the low energy physics of the model. And so I forgot to tell you that the Hamiltonian that we wrote there is really quantum Hamiltonian because the phase difference and the number of Cooper pairs inside this superconducting island do not commute with each other. And in particular, these Q, C, C, and phi obey this commutator relation. So that essentially you may consider this QCC like a momentum and this phi like an x. And now allow me to change this sign and actually to do this transformation to this sorry, let us consider the sign easier. Now I'm saying that this EJ is strong, but this EJ, we consider this as a position, corresponds to a potential energy. So that I may plot this potential energy, V, as a function of phi, and you will obtain that this is a cosine, so that in 0 this should be minimized, and in phi it has another mean. So, of course, this is a cosine potential. If you approximate it with a parabola, you understand that this is an harmonic oscillator essentially, and there will be some discrete spectrum appearing here. And this discrete spectrum corresponds to wave function in x or in phi, which are pretty much localized around the minima of this potential. However, we have a finite probability of tunneling from this state to that state. And this probability goes like this exponential tail of this ground state inside the other minimum. So this tunneling may be understood semi-classically like something that goes like that. This is the function of phi in the phi, where I am telling you that C as a function of phi will be imaginary, and it will be essentially I square root of j over 4c times 1 minus cosine of phi. And then I will have some term which depends to these two terms. Let us put this equal to 0. I don't care of that. There will appear this theorem. So the standard operator, if you do this integral, becomes equal to the minus square root of ej over ATC actually, and then there is a phase which is simply I Q M over 2 times 2 pi, because I'm doing the integral from 0 to 5, so I want to go from here to there. So at the end of the day, if I consider this part of the spectrum, which is separated by an energy scale that goes like square root of the DC in this gap, you obtain that you may represent this Hamiltonian like T plus T dagger for the two almost degenerate states which are here and are characterized by two different values of this permanent quantity. And this is proportional to this E square root of j over 8 E C times, here I will have this cosine of pi of qm, but this is nothing else than I gamma left. So you will obtain an effective Hamiltonian for the two degenerate ground states which will be here, that tells you that these two degenerate ground states are separated by an energy scale that is exponentially suppressed in this ratio Ej over C. And at the beginning I told you, oh, listen, Ej over C is very big, so that this is very small, they are almost degenerate. But this is not the end of the story, because experimentalists are very clever, and they may substitute this single Josephson junction with a split Josephson junction, which is an object done in this way. It's essentially a squid for superconductivity, where here I can put a magnetic flux. Once I do this modification, I obtain, if these two junctions are equal, I obtain an effective Ej, which will be some Ej0, which is this tunneling, times the cosine of this magnetic flux, which is measured again in terms of Hc over 2. So, the power of this thing is that in a lab, you can really switch on and off this magnetic flux as you wish. It's something easy to do. It's something that you can microscopically control. And you see that this Tj depends on this cosine, which means that I can consider this phi p equal to 0, and I'm maximizing this Ej. But if I put phi to b, which goes like goes towards pi over 2, I'm switching off this Ej. And this has big repercussions into this term, because you see that the dependence on this Ej is exponential, so it's unable to vary this term easily. I am varying this interaction over several orders of magnitude, actually 4 orders of magnitude. magnitude. So I can really switch on and off these interactions between the two Majoranas in this small superconducting island. And yes, in the end of the lectures, I told you that the trick to move Majoranas is actually to control their interaction. And this is one of the main tools that we have at our disposal to really manipulate Majoranas inside these superconducting islands. So, I don't have much time left, but I want to show you a little bit what one can do with these interactions and these Majoranas of the superconducting islands. Essentially, if we want to prove the existence of non-abelian statistics, we must be able to break them. And to break them, I already mentioned that we must engineer some geometry that works like a T-junction. And in particular, we may think about creating three of these systems with tunable interactions that can be described like this island, then we have another island here, and a third island here, for example, where I can independently tune these magnetic fluxes and thus the interaction between these six Majoranas. So I can really control this interaction, and the other interaction. However, so among the same superconducting island we will have this tridimensional interaction. Among the Majoranas that are on different islands, if I put them close enough, I will have the other tandem interaction driven by the fractional Josephson junction. And I can demonstrate that this system, under a sort of renormalization condition or perturbation theory, can be mapped in a system where I have four Majoranas, where this central Majorana is a linear combination of these three, and these external ones are essentially these three Majoranas. And the interactions here goes like the interaction there, so delta left, delta right, delta center. And this interaction I made too. Essentially, if you look at this system from the perspective of non-abelian unions, I'm saying you that here I have three Majoranas, and if I am far enough and I do not distinguish the linear structure, these three Majoranas must fuse into a single Majorana. And this single Majorana is what appears here. So, now the trick would be to analyze this braid setup, and well, there are several ways to do it. Unfortunately, I do not have the time, but yesterday we spoke a lot about these non-abelian ionic chains, and I may represent these four Majoranas inside such a chain, essentially, where I can consider a basis to describe them, which is gamma left, which is gamma right, and then the gamma central, and then the gamma bottom. So here we will have some first degree of freedom, and here we will have the total fermionic quality of the system. So this is the fermionic quality of the first two Majoranas. It is what I called I gamma left, gamma right, and this is instead the product of all the four Majoranas, which is a conserved quantities with respect to these interactions. Now, I would like to write this Hamiltonian with tunable interactions as a function of these objects. And you may see that, well, the interaction between gamma C and gamma B is pretty simple to write it down, because you just consider the difference between AY and A dot, and you obtain what is this fermionic parity. So you have an easy understanding of what is this fusion rule. So if you add some energy, you can easily calculate it. Instead, to calculate I gamma R gamma C, you see that we are in the wrong basis. And I told you yesterday that in these cases one must apply some F metrics to obtain this interaction. However, I have some way to write down this interaction. So the interaction that I'm calling delta gamma gamma C can be also written in terms of the F matrices that we saw yesterday. So we take this, the -1 and this, and in particular I must take A1 to the identity, and then the identity to A1 prime, and this is the matrix A1, A1 prime. For gamma L, it is more complicated, because to couple gamma L to gamma C, I have to change the basis by braiding these two objects. So what happens is that I, gamma L, gamma C, will be equal to the braiding between R and left, the -1, then this term of the interaction, which I call R, and then the braiding in the opposite direction. So I have that if I write down the Hamiltonian of these four objects in this basis, there appear a braiding element inside the Hamiltonian. And this is the key to obtain the braiding by tuning these objects. Essentially, yesterday I was summarizing that to do the braiding. I have to start from a situation in which gamma left and gamma right are left unpaired, and I am coupling strongly gamma C, gamma B. In this case, these two fuses are into the vacuum, so they have a fermionic parity which is gamma C, gamma B is equal to +1, whereas these two gives me some degeneracy. I can switch off this interaction because of this ability of tuning everything explanation. Now I can adiabatically switch on this interaction and switch off this other interaction. And the effect is essentially to have copied the information from this site into this site. And let me repeat this process 3 times in such a way that I am defining a path in the parameter space. So if I consider this Hamiltonian that has 3 parameters, H, delta left, delta right, and delta bottom, these are the 3 interactions. I am starting from a situation in which H of delta left is equal to 0, delta right is equal to 0, and delta bottom instead is different from 0. Then I move from this point in parameter space to another point in parameter space where instead I have this coupling which is strong, so delta left is strong and the other two are 0. Then I move in a third point in parameter space where instead this is weak and the strong one is this one, H 0, delta right 0, and finally I go back. This is the adiabatic cycle that I want to do. And the trick is that the Hamiltonian H1 here and the Hamiltonian H2 there are not really independent because of these relations that I try to sketch very fast. And in particular, you have that the Hamiltonian H1 is equal to R to the -1, between left and right. H2 R to left, right. So there is this equation that maps the points in this path to the points in this path. This means that if psi is an eigenvalue, a ground state of H1, then R L of psi is a ground state of H2. So this means that here I start from psi, which is the ground state of this Hamiltonian here, one of the two ground states, and I come back from this cycle with left, right side. I obtain the braiding that I wanted to obtain. So here I'm a little bit cheating you because these things may fluctuate, this mapping can be broken, but if you do everything carefully and you calculate the barrel phases along this path by considering that the basis that you choose to calculate this barrel phase does not change here and does not change here, so there is some continuity in the way of describing the wave function of the ground states in this cycle, you obtain that the only important thing is from which direction left the first point and in which direction you go back to this point. This is a complicated demonstration. You can either do the calculation in some interesting cases or be very careful in the demonstration. The interesting thing is that this same mechanism applies for a big number of non-abelian elements. In particular, it applies every time I have these interactions. These interactions favor a fusion. So usually you have some fusion rule, A plus V equals V plus V plus etc. etc. And these are non-abelian, because actually I'm taking them to be all equal, and instead this may be either abelian or non-abelian. The interaction that I'm putting here for Majoranas is favoring essentially the fusion into the vacuum sector, the one with a trivial fermionic parity. So every time I do this and I favor the vacuum sector, I may obtain that result. And every time I favor an abelian sector in general, I still may obtain that result. So this applies, for example, to generalization of the Majoranas that are called fermions. This applies to generalization of Majoranas including the Fibonacci, that are the SU2 level K anyons. Every time, however, that the interaction favor an abelian channel or the identity is better. If you do not have this condition, this does not work anymore because the degeneracies of the ground state of your Hamiltonian changes during the adiabatic cycle. So the key point is that if you consider in each point of this cycle the spectrum, we will have two degenerate ground states for Majoranas that are characterized by the same total fermionic parity and a different degree of freedom. So really you can also imagine this as being for Majoranas we are talking today, we are fixing this to be 0, and we are left with two systems. These are the ground states of this Hamiltonian, and during all this adiabatic cycle, their energy remains lower than the energy of the other state. This gap never closes, this degeneracy is always present. That's why I can do an adiabatic calculation and 5 minutes. No, I have a question. Oh, okay.
I mean, if you, in general, if you want to have non-abelian statistics, you have to have degenerate states.
Yes.
How do we know that this degeneracy is robust to some any kind of perturbation?
This is a very good point. So I know that this degeneracy is not robust. So for Majoranas, I know that this degeneracy is not robust if I change the fermionic parity of the system. So if I have in my Hamiltonian at a certain point some term that has a single Majorana entering there, this may essentially flip between one ground state to the other, and I totally lose control of. So in this case, the physical answer is that we are protected by a gap, which is the superconducting gap, because the superconductors avoid that spurious fermions enter in this system. But this is true only on several on a certain time scale, which is of the order of milliseconds. After a millisecond, I know that it was possible. In general, for non-abelian anyons, this is a complicated question, and I cannot really understand. I cannot really answer. But I would say that if you consider a fractional quantum setup, and you have these 4 anyons that are isolated from the rest, So as long as you do not have other aliens interacting with them in such a way that this may change the overall topological charge of the system, you are safe. But as soon as you have some edge which is close enough, or some other impurity that is close enough to the system that you are trying to manipulate, then the information is lost.
Especially if you have this engineering of different, the system is made of different islands, like you propose.
Yes. Yes.
And I don't know, even a small electrostatic energy could break.
No, the electrostatic energy does not really play a role because we are in this transmon regime, and essentially we may have this fluctuation of the Q induced in the superconducting islands, but this is not dangerous because it gives essentially an overall phase, an abelian phase at the end of the day. So here I obtain this rotation up to an abelian phase that I cannot totally not control. And if I vary this Q ind, I just influence this phase and not deliberate. What is dangerous is if something flips on the Y or on the superconducting, on the topological insulator edge. And so you have to be careful because essentially we have the three islands, and for each island there will be some probability, let us say P, that I have some noise that brings me out because I have. And you may consider these time scales for this P, so the inverse of these energies, and I told you it's of the order of milliseconds. Actually, however, we estimated that we can perform this adiabatic motion on a time scale which is, let's say, 0.1 or 0.2 microseconds. So we still have 10 orders of magnitude in time in which we may perform this adiabatically, avoiding this cosmic hypothesis. These are rough estimates, and we also analyze another situation which is dangerous. Let us say that here we have fluctuations of the superconducting parameter or of the potential, as the one that you were mentioning before, such a way that there appear an additional pair of Majorana that are strongly interacting. So you may wonder if this breaking property is stable against this sort of noise. And the answer is that it is stable as long as these Majoranas are far enough from the computational one, essentially. So in that case, we have some numerical estimation of what is the entity of the noise that breaks totally this. So, of course, it's not really topologically protected. You have to consider a set of noise. But the important thing that I want to give you as a take-home message is that since we are really able to tune this interaction very efficiently, we may manipulate these on timescales, and we may expect that in such timescales the information is preserved. Actually, if you consider the usual superconducting qubits that do not have Majoranas, these superconducting qubits have a time life, a brilliance time, which is 10 microseconds. And with Majoranas, we estimated that we can, on one side, do the operations on a timescale which is smaller than this one. And on the other, we may expect that the coherence time for topologically protecting information, let us say, is on a timescale which is bigger than this one, but smaller than this 1 millisecond that it's ultimately due to Pasquale poisoning. So we hope that the information that we put in these Majoranas is in this time interval, and however, in this time interval you see that you can do an acceptable number of operations. Then you have to go to a correction, and like in the first lecture I told you that there are ways to stabilize this information. So, well, I think that I must conclude here. The end of the story is that, however, this structure of the blade can be scaled. You can try to engineer systems with a huge number of these superconducting islands. You can try to think about tuning a lot of these parameters, and in this way you are able essentially to, well, in principle, construct without any specific theoretical limitation small quantum memories up to 10 topological qubits. And this is a work that we wrote, and it was called RAM, Random Access Majorana Memory. And well, thank you for listening to us. If there are questions,
there will be question time.
okay, esatto.
It's not